Yes, thank you very much for the invitation. As I said, please just feel free to interrupt me anytime. I don't have a plan. I need to go through the end of these slides. I would rather prefer to have a conversation because this is, I should not just have written joint work. This is ongoing work. It's the very first time I'm talking about this. I'm very excited about this and hope to get you guys excited as well. So that would be my main goal, would be to get you excited about this topic. So the collaborators here are Marvin Hahn, that I guess some of you knew, and I think he even spoke at your seminar before, who is currently in Dublin. And then Orlando Marigliano, who's also with an algebraic geometry background. And the last co-author here is Tomas Pajdla, who is an engineer. And he's a very, like in the engineering community, a very well-known computer vision engineer, but has no background at all in algebraic geometry. Okay, so what do we do? So the engineer is an engineering problem that sort of has motivated this. And the engineering problem is the following: how to model cameras that we actually all use today. Like in your smartphones, your camera is a rolling shutter camera. And also essentially everywhere else, every camera is a rolling shutter camera because they are cheap to produce. Now, what does that mean? You think of a camera taking a picture by just, you stand somewhere, you take a picture of a scene, like here is a scene on the left, and you think that the picture is taken at a time instant, and then you just get a 2D picture. But that's actually wrong for these rolling shutter sensors. Rolling shutters, they scan across the scene in a very short amount of time, of course. But if you have objects that are fast, like in the scene here, and you see what's happening, when such a camera takes a picture of a moving scene with sufficiently fast movement, then it maps lines to curves of higher degree. Yeah, so in my talk here, this is the algebraic geometry seminar, cameras are algebraic maps. They're rational maps, but they are very, very interesting rational maps, namely that they map lines to higher degree curves and sort of not what you would think mapping lines to lines. And moreover, if I capture the scene here until the end, then you see something very funny happening. So sort of the green part of the propeller actually appeared twice. And that means that these are maps that take, a single point and map it to sort of like an unordered set of appearances of that same point on an image. Does that make sense? Is there a question about sort of the problem? Or a question about what rolling shutter cameras are? So let me reiterate, almost every camera that we have today is actually scanning in a very, very short amount of time over a scene when it captures a picture. And the engineers want to model these cameras as rational maps to have something to feed to a computer. And the question is how to do that in a mathematically meaningful way and in like an engineering meaningful way. And as that, these are maps that map, single points in P3 to several points in general, and that map lines to plane curves of higher degree. And why do we want to do that? Because so the overall goal that I don't get to talk about today, because I think it would require several years of research to actually get it working, is that the engineers want to do the reconstruction of three-dimensional scenes from many pictures, where the pictures are now coming from these rolling shutter cameras. So this is a technology that exists sort of under the assumption that you don't have fast movement. It exists and works very well, but it does not work at all, essentially, only in very restricted cases for these rolling shutter cameras. Okay, and so this is sort of the long-term goal why we want to work on this. But before we can even talk about reconstructing things, we first even need to understand what are these cameras and how do they even take a picture. You know, it's like I'm thinking of taking a picture means sort of a forward map. You just need to find a map that describes this process. Reconstruction would be to compute like fibers under that map. So step after this one. Okay, so that's what we're going to talk about in this talk, is sort of trying to understand how they take pictures. So to get started with some algebraic maps here, this is the baby example. The global shutter camera is kind of the opposite of the rolling shutter camera, which is sort of the camera as you expect it to be, that would just take a picture at the same time instant. Or what such a camera is doing, you know, if you assume your coordinate, I mean, these are engineers, yeah, so they assume that they make a choice of coordinate system and blah, 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 and that you exactly project a point in 3 space onto a fixed plane that is called H here in this picture, which is the plane where the last coordinate is equal to 1, and you just do the projection through the origin onto that plane. That's what they think of as a global shutter camera. So projectively speaking, using projective geometry, that is simply the map from P3 to P2 that omits the last coordinate. Okay, and that would be one specific camera. Now, you can take as a definition that the so-called calibrated global shutter camera, what means that it's a camera which is obtained by translation and rotation from the standard one. So this definition is really like the standard choice of camera model in almost all 3D reconstruction applications that are successfully used in practice today. They would always assume that a camera looks like in the picture, but then you're allowed to translate and rotate the camera, and that it would also translate this plane H with it. So if you can also write this down, in general, this would be maps still from P3 to P2, and there would be linear maps. So in particular, they would map lines to lines and a single point to a single point. And this map, thinking of it as a matrix, it would sort of consist of a rotation matrix to model how the camera is rotated relative to the standard camera in the picture. And it would also consist of a vector C, which is the camera center of the new camera. So how the camera has been translated in comparison to the camera up there. So it's very important that we sort of all understand this slide. So if there's a question, what's be good time now? So think of a global shutter camera simply as a linear map from P3 by P2, given by a matrix of a certain shape, involving SO3. Okay, and now we sort of want to understand rolling shutter cameras. And here is now a sort of more mathy approach to defining those. So these are now, as on the previous slide, they're kind of similar to these global shutter cameras. But they move, so the camera center is moving in time. At the same time, there is a possible rotation happening of this image plane that was called H before. This plane moves with the center, and it also is affected by rotation. And there is this blue line, this rolling shutter that scans across the image plane. And at every point in time, you are just capturing that part. So at every point in time, you only can capture what is sort of hit by these orange camera rays at that point in time. So you see that this becomes a little bit more complicated than on the previous slide. So to make life a little bit more easier, common engineering assumptions, also this is how you typically build it, is that this shutter is sort of moving with constant speeds across the image plane. So I'm always trying to say everything once in an engineering term here, and then what it means for algebraic geometry perspective, okay? So the engineers like to think that this moves with constant speed. And that means that yeah, I mean, there's a bijection between how time passes and this rolling shutter position. So I can as well just identify time with this rolling shutter position. Okay, and you could make a choice. I am making a concrete choice here. Sorry, there's some noise in the background here. So this would be one concrete choice. If the rolling shutter is on the image plane, always parallel to the y-axis, then this would be in projective coordinates here. So vt is my time parameter somehow, and yeah. So my wedge symbol is for the span between 2 points, and then in dual coordinates, on the right-hand side, this would be the coefficients of the equation of the line. Okay. Then what more ingredients do we need to model this camera in the picture? So we sort of have fixed, if I go back one slide, we have sort of fixed how this blue line moves across the image plane. This is what this map rho is doing, rho for rolling shutter. But then we have to fix more stuff, right? We have to sort of fix how the center moves and how the center rotates. And since we have to deal with rotation, it's a little bit tricky here to do this projectively. So let me go to sort of the obvious affine chart. Yeah, so that when we're sort of not at infinity, then I have some sort of affine map, yeah, from A1 into the camera position called C. That's the camera center and the rotation at a given time. Now, another common engineering assumption is that this map C that gives us the camera center position, that is a rational map. And of course, if you think of a camera which is mounted onto a car or a drone, that is of course not globally true. But yeah, I mean, you either way need to think of like Bezier curves and do in some sort of, it's a very fast process how it sort of a picture is taking. So there's just a very short time span that you need to capture an image, and so we're sort of assuming that our camera moves along rational curves. Does that make sense? So one word of warning here is that we might want to assume that this map C that gives us the camera center positions is a rational map. But in general, we sort of actually do not want to assume something like that of the rotation map R. Yeah, so that can be, yeah, I'm going to say something about that later. Okay, so do we agree that this would sort of give us the data for a rolling shutter camera? Because I have told you how the blue line moves across the image plane, and at every point in time, I have also given you a camera center, which I assume varies rationally, and I have given you a rotation at each point in time. So then we sort of have a model of such a camera. Now, the question is, how does this camera actually take a picture? And at every point in time, I already said that the camera does not sort of see the whole three-dimensional ambient space. It only captures one of these orange planes. So with the orange plane, I mean like a plane spanned by the camera center at the point and a blue rolling shutter line, and it has all these orange camera rays on it. Okay. So at a given time, we can only observe such a plane, and we can, of course, easily compute it. This is now just linear algebra, because, I mean, that is it would map always the orange, I call these rolling planes, onto these blue rolling shutters, just via the matrix that I have given at each given time. Remember, this was from the global shutter definition. So at a given time, my camera is this map from P3 to P2. So it's given by a 3x4 matrix, and that's the matrix. Depends on the rotation and the camera center. So that means that if I know the blue line, which was given by this vector as one concrete choice, then I can compute the plane just as taking the pre-image under this linear map. So what I now can do is, given how the rolling shutter, the blue rolling shutter moves, and given rotation and camera center at each time, we can compute these orange planes. That's very nice. And if I want to take a picture of a point, I need to figure out which of the orange planes contain that point. Okay, and so that is actually not so easy, because now you already see from the algebraic geometry perspective, if I am giving you a family of planes and I'm giving you a point, then de facto there's in general going to be several planes, a finite amount, but several planes that contain the given point. That would just be the degree of this curve that comes from the planes. Okay, so since it's not so clear to find all those planes, maybe I want to sort of do the inverse approach, and I want to understand, if I go back to this slide, what I did here, I sort of took a blue line on the image, and then I computed its pre-image. That gives me an orange plane. Trying to talk here in colors, since I'm not in person, I cannot point at things so easily. Now I want to have a pixel, a single point on the image plane, and compute its pre-image. So sort of computing pre-images under these rolling shutter cameras is easier in some sense than to compute images. Because again, given a point in 3 space, there might be several planes that contain it. But given the point on the image, I can think of the line that maps there. And that's one way of how engineers like to do it. Of course, if you think of points in pixel coordinates, you have an x coordinate and a y coordinate, and the rolling shutter is this blue line that sort of over time rolls over the image plane from left to right or right to left. Then you could do the same thing with an orange line that moves now from bottom up or something like that. Yeah, so would be parallel to the x-axis, and then every point is just an intersection of such a blue line and a green line. And so we're thinking of the image plane from that perspective, not really as like a P2, but rather as a P1 times P1, right? Because I would always specify a blue line and a green line intersect them. That's how I think of my pixel coordinates. That's what this means. So now, given such a point on an image plane, which is a P1 times P1, and it has like a blue coordinate and a green coordinate, I want to compute the orange camera ray of all the points that map there. And that's again just taking sort of the pre-image under this this 3x4 matrix that models the camera. And so here is a final map. It's a beautiful map that we can study as algebraic geometers that would sort of eat pixels. So it eats a point on the image plane and it outputs a line. So here Gr stands for the Grassmannian of lines in P3. And so that's one of these orange lines from the picture. The orange line that contains all the points in the ambient space that get mapped to that fixed image point. So that map we can write down. Now, I hope that there's a question, because there was quite some technicalities going on here directly at the beginning of the talk. Everything's super crystal clear. Okay.
I think so, yeah.
Very nice. So sort of the message is that it is actually easier, given the point on the image, you can explicitly write down a map that computes the pre-image of an image point. But you cannot easily write down a rational map that eats a point in 3 space and then produces its image, because that image might actually not be a single point, but several points, as we will see. And so you would have to work in like unordered copies of the image plane to write that down. Okay, and so the common assumption I told you earlier, you might sort of, we want to assume that the camera center varies rationally. We do not necessarily want to assume that about the rotations, but what we want to have is that this map lambda here, that is a rational map. As I said, it's kind of, it's not really the picture taking map, but kind of its inverse. But we kind of want the picture taking to be like a rational process, so we can write to a computer, like in a nice way, how picture taking works. And things are much easier when we have rational maps. Okay.
Can I ask something? So like how, so here you are taking the image as a plain image. So it's like how different will be if you, so you said it's really hard if you have like a 3D thing to model. But then in reality the camera takes a 3D thing. No, I mean the image is a 3D thing. So how different, or the error, how bad could be?
Oh no, I mean, I am very close to modeling the reality here. So I mean, in reality, every image is a 2D thing, right? Because if you print out a picture, or you have a picture on your phone, that's a 2-dimensional thing. That's the image plane that I'm talking about. That 2-dimensional image plane is your
okay,
screen
so like
of your
it's
phone.
like the screen image.
Yes,
okay.
yes, exactly. So this map lambda, it eats a pixel on the screen of your phone. Okay. And it outputs a line in 3-dimensional space, namely all the lines. So that line contains all the points in 3-dimensional space that would get mapped to that pixel on your phone screen.
Okay, yeah, now I get it. Thanks.
Exactly. Yeah. So we're sort of, as I said, we're not really modeling how to take a picture, but sort of the inverse of how to take a picture here. Okay. So now let's actually try to understand how to take a picture. So let us understand the image of this map lambda. I mean, it maps P1 times P1 into the Grassmannian. So we expect the image of this map to be a surface in the Grassmannian. And these are, in the old literature from Kummer times, they are called line congruences. Okay, and so I'm always writing now L for this line congruence, which is the surface in the Grassmannian, and that is the risk closure of the image of this map. So it's the set of all these orange lines. I cannot obviously draw all of them. I'll just draw a finite sample here. But if you think of it, there's a 2-dimensional family of orange lines, and that family is the line congruence. Okay, and then, I mean, now a surface in the Grassmannian has a sort of bi degree. So the order, so typically one talks about the order in a class of the congruence. And so the order of such a surface is the number of lines, orange lines in my picture, that pass through a generic point. The class would be the dual notion, the number of lines contained in a generic plane. And so if I just send you a surface, the Grassmannian, via email, you know, that order is some number. That is not necessarily 1. But that number essentially captures how often the rolling shutter camera is going to see a point, but almost. Because here is in fact the statement, if you think about it, how often a rolling shutter camera sees a generic point is the order of its congruence times the degree of this map, lambda. Because if a generic point walks through the door and the camera looks at it, then you first have to ask yourself how many orange camera rays pass through it. But now each of these orange camera rays might actually be seen on several pixels on the image. That would be the degree of lambda. So how often a point is seen by the camera depends on two things: the order of this algebraic surface in the Grassmannian, and also the degree of its parametrization map. And so we call that product the order of the camera. I hope that makes sense. And so you see that that's why it's not so easy to write down a nice map that eats a point in P3 and then outputs its image, because that image is going to be several points in the order many points. And so you would have to work in the order many copies of P1 times P1, and they have to be unordered. So yeah, that sort of situation. Okay, and so since it's kind of tricky to deal with cameras of general order, in the current project we're doing is that we're really gonna we're still far away from the final goal of doing 3D reconstruction with rolling shutter cameras in general. Yeah, so what we're doing right now is we're just focusing on cameras of order 1, because then that's actually something that we can try to actually do 3D reconstruction with. But even there, we're not there yet. Maybe next year. Okay, so let us understand cameras of order 1, because then I can tell you very easily a rational map that eats a point in P3 and outputs its unique image point. Yeah, because if I have order 1 in this previous, well, I didn't call it a theorem, but it's proposition or whatever, if this number is 1, then both the map lambda has to be birational and its image surface has to be an order 1 congruence. Okay, I'm just using that. So since the map lambda is now birational, we can invert it. There is now a map that goes from the congruence into P1 times P1, that's nice. And second, that image congruence has order 1. Definition of order was again how many lines on the congruence pass through a generic point. Now there is a unique such line, and so you can write down a rational map that, given a point x, it writes down the line that passes through x. Okay, and now if you just compose these two maps with each other, you get an actual picture-taking map. So first, eating a point in P3, you assign the unique line on the congruence passing through it, and then you use the inverse of lambda to map that to the unique pixel, so the unique point on the image. Are we good? What time is it, yes, by the way? I also don't see the time at the moment. I didn't bring my phone.
You still have a good half an hour. So.
Okay. Very nice. But this is sort of the first thing that I want to tell you about. So we're doing this project. It's going to be like a long-term thing going over several years. And yeah, so this is really the sought after technology. Like we are also talking to Volvo and so on, like their self-driving cars, kind of, you want that. But yeah, sort of I think you need a more deeper geometric understanding of the problem, because only keeping on engineering this problem sort of hasn't helped in the last 10 years that people try to do it. Okay. So let's talk about this order 1 cameras a little bit more. And just sort of, we have seen already an order 1 camera, because every global shutter camera is that, you know, I can think of a global shutter camera as a rolling shutter camera that doesn't move, because if the camera doesn't move, then it doesn't matter that it sort of captures the image row by row. And this is in fact a order 1 camera, because the congruence associated to this global shutter camera is just all lines passing through the fixed camera center. And so this map that eats a point in P3 and assigns the unique line passing through it is simply taking the span of the point X with the camera center. So that's all very, very easy. But it's a good sanity check. So the congruence is order 1, and I'm telling you this map gamma, I call it here, that shows us that it indeed has order 1. And this lambda inversion would just take all the lines on the congruences and cut it with a fixed image plane. Yeah, and so that's all very easy. Okay, so now that we understand how one can model rolling shutter cameras kind of in general, and we understand a little bit about how often a point can be seen by such a camera, for the sort of task of 3D reconstruction, I also need to be able to send to you order 1 cameras if I want to do 3D reconstruction with order 1 cameras via email, right? I need a moduli space somehow of these cameras. Because the goal in 3D reconstruction is that you just have given a bunch of pictures, you do not know the cameras that took it, you want to reconstruct the cameras and the 3D scene. So you need to have the space of cameras to work with. And so that's what we're working on at the moment, or for a while already. And so I want to tell you, how can you tell when a rolling shutter camera has order 1? And that is connecting to Kummer's beautiful results that I had advertised in my abstract. So how does this go? So here is again the sketch of a rolling shutter camera. And to recall notation, I have this map C that at every given point in time gives me the position of the camera center. And then I have also at every given point in time, I have this orange planes, yeah, which are unions of these orange camera rays. And so I call this small sigma is called here the map that eats a time parameter and outputs the orange plane at that time. And then we can say that the camera has order 1 if and only if some very nice conditions hold. So first of all these orange planes, so over all the times, all the orange planes, they have to meet in a common line. I'm going to call this line K. It's very important to give that thing a name. So that means, in fact, that this map sigma, it's a map from P1 to P1, right? Because all the planes that contain a fixed line, that's a P1. So this rolling planes map that eats a time parameter and outputs a plane, I can write it like this, you know, K dual, here's my notation for the lines, the planes that contain the line K. And I do not only want that all the planes contain that line K, but this map from P1 to that P1 is in fact a birational map. So it's very strong what it means to have order 1. We already see that. So the rolling planes have to meet in line, and that assignment of time to these planes has to be birational. And then there's also restrictions on what the curve traced by the camera center can look like. Namely, there's 3 cases, and here is all the 3 cases. Either this curve is a curve that meets, if the curve has degree d, then it should meet the line K in d minus 1 points. So that's a very, very special type of curve. Okay. Or the curve is allowed to be equal to the line K, or the curve also actually be degenerate to a point. So it could just not be a curve, it could just be a single point on that line K. These are the 3 cases. You see, this brings us again to interesting questions, namely, studying the space of curves that meet a fixed line, you know, in super many points, etc., etc. So that's the structure that we have here. We have seen an example of this very, very last type already, because there was this picture of like these global shutter cameras, and they have like a fixed camera center, so they would be of that shape. And this theorem explains how all order 1 cameras look like. And so essentially, there is some work involved, but the key ingredient for that result is this theorem by Kummer. And then many people have made his proof a little bit more accurate. So this is actually by Depart, like the formulation here is not exactly how Kummer wrote it, but yeah. So in any case, the result says that a surface, say irreducible algebraic surface in the Grassmannian, has order 1 if and only if it's 1 out of 4 cases. And I wrote here 4 cases, and these first 3 cases correspond exactly to the 3 types of the rolling shutter cameras. So let me just walk this. Type 1 means that the congruence comes from all lines that meet a rational curve C and a line K, with the property that the line K meets the curve C in D minus 1 many points, where D is the degree of the curve. Then the second thing is a little bit difficult to pass when you see it for the first time. It's a little bit difficult to wrap your head around what that means. But the second type that Kummer classified was, there is a line, K, and then you have a dominant morphism from the planes that contain K onto the points of K, such that your congruence is a union of pencils. Namely, it's it's the union, and so the pencils, they're sort of given by a point on the curve K and a plane. So the sigma here is a plane containing K, and then for each such plane you have this kappa of sigma, which is a point on K, and then you consider the pencil of lines passing through that point contained in that plane. You take the union of all of those. In any case, I want to state this theorem for completeness the way it is. So the third case is now much easier. The congruence could just be the set of lines passing through a fixed point. We already have seen that congruence for the global shutter camera, as I said. And then there's a fourth case, namely the congruence could also be the secant lines of a twisted cubic curve. But it turns out that you can show that this last type, secant congruences of twisted cubic curves, they can just not arise from rolling shutter cameras. And then you have to make some work to put these other 3 conditions into the 3 conditions of the previous theorem. And we don't just want the congruence to be order 1, but also this lambda map to be birational. Is there a question or comment here? Would also be a good time.
No
Very
comments.
nice. And let's see what I want to do next. So now we have a theorem on how order 1 cameras look like. Yeah, these orange planes have to meet in a line. There has to be this birational map that parametrizes, and our curve where the camera moves is also very restricted. Okay, and so what we want to do, or what we're working on right now at the moment, is, as I said, we want to have sort of moduli spaces of rolling shutter cameras that sort of would cover all possible rolling shutter cameras. Because again, for 3D reconstruction, the rolling shutter camera would be a data point that you would have to recover. So we have to be able to have a nice parameter space so that we can write down these cameras. Okay, and so it's not so clear actually how to do it. Because you can say, of course, as the sentence here in general says, a rolling shutter camera is sort of given to you. I could send the camera to you by sending you the map C of its how its camera center moves, and I could also send you this possibly non-rational map that gives you the rotation at each point in time. But then I have only given you a camera, not generally an order 1 camera. And so our theorem doesn't really involve these rotations. So the question is, how can I make sure that I send you cameras, or how can I send you all cameras of order 1? And yeah, so there's these 3 types from the theorem. So one could look at type 1, which is sort of the more general one. I think it should be true that if you think in terms of moduli spaces, that sort of type 2 should really be like a degeneration of the type 1, and then that the last type 3 is a degeneration of that, but it's not so clear yet, I think. I'd be happy if someone's interested in these moduli space considerations. Okay, so let me just repeat for you here what type 1 means. I want to sort of find a space of order 1 cameras, and type 1 meant that all these orange planes near line K, the map parameterizing these planes is birational, and the curve where the camera center moves is a degree D curve that meets the line K in D minus 1 many points. So let me start by sort of this last ingredient. People have studied this space, I call it HD, which is pairs of curves, rational curves, and of degree D, that's the D in the index, and lines that are D minus 1 secants. Okay, so that space has been studied in, as I said, various works, various aspects of it. And yeah, so this is a space of dimension 3D plus 5. And so in particular, for any curve of degree at most 5, you can find such a line that is a D minus 1 secant. And then for curves of degree starting from 6, then for general such curves, there is no such line. I mean, so this last bullet point here just follows easily from the dimension argument. If you believe that the dimension is 3D plus 5, but the space of rational curves has degree 4D. Yeah, so that there's a dimension difference starting from 6 simply. So that means, but this fact, as I said, I try to say things sort of both from the engineering and the algebra perspective. This fact is very interesting for the engineers already, because it tells them that for curves up to degree 5, you can use any curve to model an order 1 camera. For higher degree curves, you cannot. And it's of course interesting because in most applications, if you make this assumption that your camera follows a curve, you sort of want to work with low degree curves anyways. So it's then nice to know that you don't have any sort of restriction up first, sort of on the curve. Now, it could move on any curve, and you just have to find an appropriate line. So I already sort of talked a little bit about this now, but so just because we understand the space of these curves with D minus 1 secants, does every such pair, can it actually come from a rolling shutter camera? And the answer is, in fact, almost yes. There's just, yeah, there's a risky dense set of those, because the only thing this modeling that we would not allow to have is that neither the curve nor the line would have to be allowed to be completely at infinity. Because in this engineering application, we always have a choice of what the plane at infinity should be, simply sort of by the fact on how we model rotations into our camera matrices. So our P3 is not an abstract P3, but it's always the P3 where the plane at infinity is the one where the last coordinate would be 0. But yeah, so besides sort of curves and lines at infinity, we're good to choose any such pair. Okay, the next question is, so say I want to build a camera that moves on my favorite curve, and that I promised you this curve has such a d minus 1 secant k. Okay, now I want to build such a camera. I want to find sort of how the rotation has to be at every given point in time to make that work. And since rotations are complicated, I first want to think about these rolling planes. So this sigma was my notation for the map that at every point in time assigns the orange plane. Okay. And now, can I just choose any map if I want to build such a camera? And here the answer, it took us a moment to figure out, but is actually no. So this now just starts to be a little bit more technical. But if you want to omit the technicality, I mean, there is how many maps do you have between P1 and P1? There's a three-dimensional family of such maps. Now, what I'm telling you is you cannot choose them arbitrarily. You can only choose them among a one-dimensional family of such maps. Yeah, and so they essentially have to be very specifically written out, spanned by 2 points A and B that are orthogonal to each other. And so this sort of fact, which is algebraic in the end, but it comes from the fact that we're actually dealing with rotations here, and that rotations, that's sort of the information that a rotation carries out over to the plane as infinity, if you want. So you cannot have arbitrary birational maps. You cannot choose these orange planes in an arbitrary fashion. Okay, but if you pick a map that is good, okay, so here this sigma infinity notation is simply the intersection of an orange plane with the plane at infinity. That's an orange line in the picture. And if you have such a map, you can, of course, get back the actual orange plane by just taking the span with the fixed line k. And then you can also get back not just the curve C, but rather the correct parameterization of the curve C. Because remember, what is a rolling shutter camera? It's given by the map small c that gives you the camera center at each point and the rotation map. Now I know the map small c because every orange plane leads, of course, the curve in d many points. Now d minus 1 of them lie on k and are not relevant, and there's a unique other point, and that's your camera center. Now I know this was maybe a little bit technical, but sort of the story is here that if I want to build a rolling shutter camera of order 1 following Kummer's type 1, then I can choose sort of, I need to start by choosing a pair of a curve and a line that's a d minus 1 secant. Then I have to choose a sort of very specific type of rolling planes map. There's a one-dimensional freedom that you have of those, but we can do it. But then the rotation is still not fixed. Yeah. So at this point, I know how the camera center moves, and I know the rolling plane, so I know the whole congruence. I know the congruence, but I do not know yet the whole lambda map because I just don't have the rotations yet. Yeah, because like, what is the intuition here? If you look at this picture again, at every given point in time, you have a camera center and you have an orange plane now, but you still don't know what the rotation is around that camera center in that plane. So this planar rotation information is still missing. Okay, and so one could fix the rotation by choosing which orange camera ray gets mapped to what your favorite point. In fact, you could choose your favorite point on a given rolling shutter. And I'm choosing this point 010 because by our choice of rolling shutter, that is the unique point that all these blue rolling shutter lines have in common. because they were parallel to the y-axis, and that means projectively that they have to pass to the point 0, 1, 0. So by fixing the unique sort of camera ray that maps to that specific point in the image, I essentially fix the rotation. Yeah, and so I can do that. Each of these orange lines meets the line K, so this map actually becomes a little bit easier. We have like a rational map. It's simply given sort of by a rational map from P1 to K. K is a gathered P1, so we have lots of maps between P1s and P1s here. And this map could now be whatever, in fact. This is an arbitrary map. Okay, in fact, okay, now a side remark, I said this map sort of lambda determines the rotation, but there's in fact 4 choices of rotation by giving this. So it's sort of the true map moduli space of cameras is like a 4-to-1 cover of what I'm describing here. So here's the summary of all these technicalities I walked you through. There is a 4-to-1 correspondence between order 1 rolling shutter cameras of Kummer type 1 and the elements of this beautiful parameter space. So this parameter space R has 3 indices. The first one is capital I for type 1. Then there is D for the degree of the curve where the camera moves. And then there is a delta, because I told you this map from the previous slide can be whatever. So that's just the degree of that map. Okay. And so such a camera up to this 4-to-1 correspondence is given by this curve C of degree D that's not at infinity, that has a D minus 1 secant K, which is also not at infinity. And then we have this rolling planes map that has to be of this very specific form. And then we essentially fix the rotation by another map from a P1 to a P1, which is K. But this would give us parameter spaces that cover all these rolling shutter cameras. It's parameter spaces of a dimension that you can easily compute. Okay, now last thing I want to do is, now you can wake up. You see, this is the last slide. I know everybody is tired, and this was quite technical, but bear with me on the last slide. So I have told you what an order 1 camera is, how they can take pictures. I told you it can take pictures in a very explicit way. It eats you a point in P3 and then manages to produce a point on an image. And the question is, what does it do to lines? Because on the propeller slide, at the very beginning, I showed you that lines get mapped to higher degree curves. And now that I have the space of cameras, the question is, what happens to the image lines? So if I have a camera from the previous slide in this parameter space of cameras, then the image of a generic line is a very interesting curve. Namely, it's a curve of degree D plus delta plus 1. D was the degree of the curve where the camera moves. Delta is essentially the curve fixing our rotation. And I have plus 1. But what's more interesting is that these curves have one very, very intense nodal singularity, namely at the point 0, 1, 0, which was the point where all the blue rolling shutter lines meet. That curve has a singularity of multiplicity D plus delta. That number tells you that it can also not have any other singular points. So that's, yeah. And in fact, it's a nodal type of singularity, as I said. So even now, I kind of wanted to include a picture, but didn't have time to make one. This is sort of the example here is the easiest rolling shutter camera you can imagine, which is not a global shutter camera. So this camera moves along a line, okay, and say it doesn't rotate. But then still, if it's an order 1 camera moving along a line, doesn't rotate, it's going to map lines to conics, and the conics have to pass through the point 0, 1, 0. Okay, that's all I wanted to say.